Yeah, so welcome to this channel. Today we will be solving this question based on the application of the first law of thermodynamics, and it is based on the subtopic steam turbines. So the question is, a steam turbine operates at the inlet conditions which are given here of 120 bars. These are your inlet conditions of 120 bars, 480 degrees Celsius, 100 meters per second, and flows through an area of 100 centimeters square. And the exit gravity is at 90%. Exit gravity 90%, which is also the quality represented by X. Pressure is 1 bar and the velocity is 50 meters per second. We need to calculate the change in kinetic energy, the mass flow rate, or the mass flow rate. Sorry, there is also, this is the third part. The second part which we need to calculate is the shaft work, then mass flow rate, then power output, and the exit area in meters square. This is a very important question and usually asked in exams. So let us write down what is given. We have your inlet conditions and here you have your outlet conditions. Inlet conditions may the given is it is operating at 120 bars, 480 degrees Celsius, and the velocity is 100 meters per second, and the area is 100 centimeter square. Then outlet pressure is not known, only the exit gravity, it is given as 90%, which is also the X or the quality, and it is at 0.9. Okay, then you have your pressure at outlet as 1 bar and the flow velocity as 50 meters per second. We need to calculate the kinetic energy or the change in kinetic energy we need to calculate. So the change in kinetic energy, which is delta Ke, the first part is here. Delta Ke or the change in kinetic energy क्या होगा हमारा होता है, we do not consider mass in these. We just take V2 square minus V1 square divided by 2. It is actually half mv square, but in these properties of calculations, we do not consider the mass. Okay, so V2 square minus V1 square, which is 50 minus 100 divided by 2. When we do these calculations, we'll get minus 7500 by 2, which is minus 1350 joules per kg. It is joules per kg because that is meter per second square, meter square per second square, and it will be converted to joules per kg, and to convert it into kilojoules, we have minus 3.150 kilojoules per kg. Okay, so this is your solution to the first part, or the kinetic energy. Then the second part, we have to calculate the shaft work in the second part. So if we write the equation of the according to the first law of thermodynamics, we have that heat plus shaft work is equal to the change in kinetic energy plus change in potential energy plus your change in enthalpy. So here, as it is given in question that the steam turbine is operating at adiabatic conditions, so the this Q will be 0. Also, there is no change in potential energy in steam turbines. So these both terms will be considered as 0, and the shaft work will be equal to change in kinetic energy plus change in enthalpy. So this is your shaft work. Change in kinetic energy, we have already calculated it as minus 3.750 kilojoules per kg. And delta H is what we need to find out right now. So for delta H, we have like inlet conditions we had at 120 bars. And you have at 120 bars, if we go to our superheated steam tables, at 120 bars, it is given that your T saturation temperature is 324.2 degrees Celsius. It is 324.65 degrees Celsius. That is your saturation temperature. And what is the temperature which is given? That is, it is operating at 480 degrees Celsius. So you have superheated steam here. Okay, so superheated steam here. 480 degrees Celsius. When we calculate the value of H1 at 480 degrees Celsius, it by the interpolation method, we get it as 3292.2 kilojoules per kg. If you don't know how to do this interpolation from the steam tables, do comment down below and I'll make a separate video on that. So this is your H1. Now, how to calculate H2? Because your outlet temperature is not known to us. So how to calculate the H2 value? So we have one, we are given that at outlet, it is given that it is operating at 1 bars. So H2 will be given by this equation. H2 is equals to HF plus X times of HFG. The value of HF and HFG we will calculate at 1 bar. So at HF, 1 bar is given by at 418 kilojoules per kg, and HFG is given as 225. It is given as 2257.4 kilojoules per kg. So this we get from the pressure basis steam table. So when we substitute the value, the H2 we will be getting HF, the value is 418 plus X is given as 0.9 into HFG, which is 22.57.4 kilojoules per kg. On solving this, we will get 2449.61 kilojoules per kg. So our delta H will be H2 minus H1. What is the H2 value? What is the H2 value we are having here? So here H2 value is this and H1 value is this. When we subtract H2 minus H1, we will be getting it as minus 841.03 kilojoules per kg. So we had converted our change in kinetic energy to kilojoules per kg. This is also kilojoules per kg. So our total shaft work in this case, will be a change in kinetic energy plus delta H. So the value on adding both these values, we will be getting minus 844.78 kilojoules per kg. So with this, we solve with the second part. The third part which we have to solve here is your mass flow rate. We need to find out the mass flow rate of the steam turbine. Then for mass flow rate is calculated by the formula. It is calculated by the formula A1 V1 upon the specific volume. So we need to calculate the mass flow rate of the, what is the mass flow rate, right? So the formula is A1 V1 divided by the specific volume. So A1, it is at 100 centimeters square. What is the velocity we are having here? The inlet velocity, it is also 100 meters per second, and the value of specific volume at 480 degrees Celsius, at 480 degrees Celsius and 120 bars at 480, because when you go to superheated steam tables at 120 bars and you have 480 degrees Celsius, you calculate the specific volume by the interpolation method. So it comes out to be 2.5728 meter cube per kg. This is your value of specific volume. So you substitute this value here, 2.57 0.28 meter cube per kg, and this second comes here. This centimeter cube to be converted to meter cube, we need to multiply it by 10 raised to the power minus 4 meter square. So on solving this, the units, we'll get meter cube gets cancelled out with meter cube. Kg per second, that will be the units, and on solving this by your scientific calculator, you will be getting the value as 38.987 kg per second. So this is your mass flow rate. With this, we solve with the third part of the question. Now on solving the fourth part of the question, which is your power output. Power output is very simple. It is just your mass flow rate multiplied by your shaft work. We have mass flow rate, we have shaft work. It is simple multiplication of both the values. So your mass flow rate is 38.987 kg per second multiplied by minus 844.78 kilojoules per kg. Kg gets cancelled out. We get kilojoule per second, or which is accounted to as watt, minus 32.937 watts. The last part of the question, wherein we have to find out the exit area. What is the exit area of the steam turbine? For exit area, we take it as A1 V1 by mu1 is equals to A2 V2 upon specific volume 2. So we need to calculate the exit area, and we also need to calculate the specific volume. So specific volume will be given by Vf plus x times of Vfg. These values we will be calculating at 1 bar. Specific volume values, then so for specific volume we will be getting it as 1.5245. So we will be substituting it here. Substituting all the values, we will be getting A2 as A1 V1 mu2 upon mu1. Okay, so if I help you with these value substitution, what is A1? It is 100 centimeter square multiplied by minus 10 to the power 4 meter square. What is velocity? It is 100 meters per second. What is mu2? This is your mu2 value. Okay, and mu1 is here. You just need to substitute and calculate. The answer to this question is 1.188 meters square, or which is approximately equal to 1.19 meters square. So with this, we finish with this question. Stay tuned for more such questions.